Intro to Chem, folks. We're getting near the end of our gases chapter. 2 chapters ago, we studied stoichiometry, where we related the amount of one chemical involved in a chemical reaction with another chemical involved in that same reaction. And we did a couple problems that involved gases, but now we're going to do a few more stoichiometry problems involving gases. Some review from the Stoich chapter. The mole is the bridge between calculations of particles, mass, and volume of an element or compound. We can relate moles to particles, we can relate moles to grams, and we can relate moles to liters. We cannot relate grams to liters directly or grams to particles directly. So there are 3 facts that we used in our previous chapter. The fact that 1 mole of any chemical contains 6.02 times 10 to the 23rd particles. And by particles, we mean either atoms, molecules, or formula units, depending on what the actual chemical is. We've done this a number of times. Molar mass is the number of grams in 1 mole of a compound. I cannot give you a single value for that. We must determine that by using the masses on the periodic table. And we just reviewed in this chapter that at conditions of STP, which are 0 Celsius and 1 atmosphere of pressure, 1 mole of any gas occupies 22.4 liters. If I change those temperature pressure conditions, the amount that will occupy will change. But for all our problems, we are going to assume that we are at STP and that 1 mole of any gas occupies 22.4 liters. So knowing those facts, we can use them to make conversion factors. 6.02 over 1 mole over 6.02 if we're talking about particles. 22.4 liters over 1 mole over 22.4 liters, that applies only to gases. And molar mass, some number of grams determined by the periodic table, either on the top or on the bottom of the conversion factor. So in any conversion problem, and we've done these several times throughout the year, the starting unit or previous unit always goes on the bottom of the conversion factor. And while I'm not going to be picky about this, your answer should have the same sig digits as the starting value, the one that I gave you. So here's an example of a Stoich problem. We have a balanced equation, and the question is how many liters, of hydrogen gas, H2, are produced when 1.25 moles of calcium reacts. So the equation says 1 mole reacts with 2 moles to make 1 mole and 1 mole. If you still have it in your notebook, might be a good thing to pull out to help you do these problems. Our stoichiometry map. Remember that the left side represents a chemical that I know a value for, whether it's grams, molecules, liters, or moles. The right side represents the chemical I'm trying to find a value for. And the only way I can relate the amount of one chemical to the amount of another is by comparing moles to moles using the mole ratio from the balanced equation. So our equation was saying if I start with moles of calcium, how many liters of hydrogen will I make? Well, I can't go directly from moles of calcium to liters of hydrogen. I have to go from moles of calcium to moles of hydrogen and then to liters of hydrogen. So using this map helps us plan our route to get from one place to the other. So our route is moles of calcium to moles of hydrogen and then to liters of hydrogen. This route sets up the top of your conversion series. So I fill in. I started with 1.25 moles of calcium. I want to convert to moles of hydrogen and then to liters of hydrogen. Previous unit always drops to the bottom. So moles of calcium goes down there, moles of hydrogen goes down there. Now I have to fill in the numbers for these conversion factors. Well, comparing mole to mole, I look up at the balanced equation. 1 mole of calcium reacts with 1 mole of hydrogen. 1 mole of calcium, 1 mole hydrogen, 1 mole of calcium. And for any gas, 1 mole occupies 22.4 liters. So I'm going to put this into my calculator. 1.25, I don't need to type times 1 divided by 1, but I do need to type 1.25 times 22.4 equals 64.6 liters, and that should not say nitrogen, it should say hydrogen. My apologies. Here is a second example. This is a very real life situation. The airbags in your car that you're driving, you might have passenger, driver, side airbags, whatever the heck. When you get in an accident, there's not a little compressed gas sitting under your hood that suddenly inflates those bags. It's actually a chemical reaction that instantaneously produces a gas. So those bags contain a powder called sodium azide, formula NaN3. And when the car detects that there's been an accident, a spark goes off and it immediately decomposes that sodium azide into sodium metal and nitrogen gas. So if we're going to design all these different size airbags, we have to know how much chemical goes into the bag if we want it to inflate to a certain volume. So suppose I were to put 125 grams of sodium azide into that bag. When the reaction occurs, what volume of nitrogen gas will be produced? We need it to be correct because if it's too hard, you'll hit the airbag just as hard as you would the steering wheel. If it's too soft, you'll go right through the airbag and hit the steering wheel. You want just enough nitrogen in that bag to cushion you from hitting the steering wheel. So I know grams of sodium azide, and I want to know liters of nitrogen gas. So I'm going to look at my map again. Again, I know sodium azide. I want to know nitrogen. So I go from grams of sodium azide to moles of sodium azide, then to moles of nitrogen, and then on to liters of nitrogen. So this is my path. Grams to moles to liters. Grams to moles to liters. Once I know my root, that's the top of my conversion series. I fill in my starting value, 125 grams, moles of this, moles of the other, liters of the other. In every conversion problem, the starting unit drops to the bottom of the next conversion. So grams of sodium azide, moles of sodium azide, moles of nitrogen. Now I need to fill in the numbers for these relationships. From the balanced equation, it's 2 moles of sodium azide will produce 3 moles of nitrogen gas. So I fill in my 3 and my 2. I'm comparing grams and moles, so I'm using molar mass. I add together the mass of 1 atom of sodium and 3 atoms of nitrogen, which equals 65. Because we are at STP, 1 mole of any gas, regardless of what it is, occupies 22.4 liters. Now I have a lot to put in my calculator. 125 times 1 divided by 65 times 3 divided by 2 times 22.4 equals the number of liters of nitrogen. And it comes out to be 64.6 liters of nitrogen. Okay, so those are the sample problems. I'm going to ask you to do 4 homework problems involving stoichiometry with gases. Hopefully you followed along with these problems and you are able to do them. You should have, if you've kept your notebook with your materials in it, you should have your note packet from the Stoich chapter. You should have your homework packet from the Stoich chapter. So that would provide some additional information to help you solve these types of problems.